So good afternoon. This is our 11th lecture from our computer architecture course, and today's topic is x86 architecture. So it is about this architecture which you most probably have in your laptops and computers, because maybe there are some people who have ARM or M1, for example, in Apple computers, but most of other computers has usually this x86 architecture processor. And I start with such a short overview presentation by Petr Štěpán, which has been prepared for our Czech students course. And okay, I hope that there should be a picture. Yes, it is some, again, interesting picture from the space. And we start with our x86 family. In the fact, the Intel was one of the first teams which was able to integrate a whole processor on a single chip. There has been some Fairchild before it, and then the team set up the Intel company, and they started with 4004, which was a 4-bit computer or processor or system on chip. Then they started with 8008, which has already been 8-bit, and then 8080, which was quite well known at some time, and its team then started a Zilog 80, if you know Sinclair or some another 8-bit processors and computers of that era. But what is important that in the year 1978 or 9, they started production of the new 16-bit processor. But this processor was in the fact the extension, 16-bit extension of the original 8-bit design, and this legacy is kept up today to its 64-bit variant. It starts as 16-bit first with 16-bit arithmetic logic unit, and they want to extend the addressing capability because the 8-bit processors can encode the 16-bit address, so it can encode 64 kilobytes or kibibytes of the address space. And then they want to have a little more for the 16-bit processor, so they add such system that they use a 16-bit segment which was multiplied by 16 and combined with actual pointers in the registers. So they form a 20-bit address which allows to address a 1 megabyte of the memory. Then in the next step, when already some another processor or even processors on the single silicon has 32-bit registers and addressing capabilities, Intel decides to use still the 16-bit arithmetic logic unit and extend the addressing capability to 24 bits, so this means to 16 megabytes, and use a protected mode. So they decide that they do not extend and increase the size of the arithmetic logic unit, but somehow combine segments, in this case called segment selectors, and some infrastructure which allows to do the complex addressing with protection. It was relatively unfortunate mode, and the other architecture started with actual paging, that virtual memory which we have already spoken about during our third lecture and fourth lecture. So they found that it is a problem, and the 386 chip has already 32-bit registers and 32-bit physical address capability. So, and it has a standard paging, but the protected mode has been kept, and that mechanism of different segment selectors and task segment selectors and so on. So basically they implement in the hardware quite complex logic in the fact part of operating system, which in the end is not a big win. And it is not used today. Then there was 80 and 486 processor, which starts with pipelining, and it implements a floating point unit directly on the same chip as a processor. For the previous chip, it was possible to add floating point unit, but it was 87 additional chip, which snoops the data from the buses of the processor and allows to do a floating point computation. So this was the first one where all has been implemented on the single die, on the single chip. Then the Pentium processor, which is the famous name and sometimes used like a trademark till today, was the chip which has been a partially superscalar. So it has a ability to execute, to decode and execute two arithmetic logic instruction in the single clock cycle, and it has a third queue for a floating point. So it was already a little superscalar that some combination could be decoded in parallel. Then there is 686 or so-called Pentium Pro, and instead of switching directly to 64-bit processor design, which was a standard for some big processor from digital equipment and PowerPC and so on at that time, they decide again to extend a 32-bit virtual addressing to the 36-bit physical addressing. So in one program, you cannot have more than 4 gigabytes of the addressable space. But if you have more programs, then each of those programs can use a different subset of the physical pages and utilize up to 60, how it is, 64, I think, yes, 64 gigabytes of physical memory. And they added a second level cache, and it was already out of order execution, and it was deeply pipelined, which at the end should allow a very high clock frequencies, and it relatively worked well in this respect. But it was relatively expensive at the time when you need to flush the pipeline due to the branches, and they have decided not to store the instruction for the following versions in the cache, in the original complex instruction set form, but to translate it to the some RISC version of the instruction. And at the end, those processor has not been too much useful, and they have a very large power consumption. Intel knows that the architecture of x86 keeps too much legacy, and they decide that they do not want to extend it to 64-bit, and they started the Itanium, which was very long instruction word processor, so different paradigm for implementing the processor. It was 64-bit. It has some mode when it was able somehow to do software emulation of the x86. And at the start, it was relatively slow and too expensive. Then later, they have been able to enhance the throughput of this processor, and it really proved its qualities for the large-scale computation. So in the segment of supercomputing and global clima computation and so on, it was relatively useful and powerful. But this change was too big for the standard legacy desktop applications, and they would be required to be anyway recompiled and so on. So at the end, this architecture has not catch up. And the AMD, which has a license from Intel to build a compatible processors from the 80s, and know that they would not have the possibility to get the license for Itanium chip. They decide to build their own 64-bit version of the x86 architecture. So AMD came with processor which was able directly execute a 32-bit program from the previous generation of Intel processors, but has additional mode for 64-bit. And this additional mode doesn't use exactly a totally different encoding. It uses the same encoding, extended with some prefixes and so on to work with 64-bit. And at the end, this one has big momentum and was useful. So at the end, Intel has switched to this EMT64T architecture with their processors as well. So the actual Core 2 and Core i5, 7, and so on are the processor which has abandoned the deep pipeline version of the NetBurst architecture, and instead they decide to continue from some little lightweight Pentium 2 mobile version of the chip, and continue design from this with the extension taken from AMD design of the instruction set, and those processors internally translate instructions to the micro operation or RISC-like operation. So internally, they can use those techniques which we have seen in the 5th lecture, and they add quite a lot of the multimedia support, so special instruction which can execute multiple addition or the multiplication on some wide vector directly by a single instruction. And there is added another mode for the virtualization and so on, because it starts to be heavily used. If we look at the basic processor, so initially we start with the 8-bit 8080 CPU, which has, I think, 7 8-bit registers. And those registers can be used in the 16-bit pairs. So this is the reason why we have there the AX 16-bit register on the 16-bit version, which has upper 8-bit part and lower 8-bit part. And then when they extend the processor to a 32-bit, they added another 16-bit into the register. So it starts to be called the EAX, extended AX, and it is 32-bit variant of the register. And if you work with these smaller parts of the register, then rest of the register is kept at the previous value. So you can replace the lower 16 bits. Then AMD decide, when they extend the processor to a 64-bit one, that they define a little different mode in which if you write to the bottom part, bottom 32 bits of the registers, or one or byte of the register and so on, then upper part of the registers is filled by zeros. Why to enforce the zeros in the upper part? This is a question. The reason is that they decide that if you need to compute dependencies of mutual dependencies of the multiple instructions, then it is easier if you basically rewrite a whole register. If you do not keep part of original content, Because in the case that you need to keep part of original content, then in such case, in the fact, you need to add yet another dependency. So you have one dependency for one operand, another for another operand, and third dependency for the previous value of the register. So they decide that it is better to rewrite the rest of the register by a 0, and the 64-bit register is called RAX. So you can access to all those registers by different mode. In the 64-bit mode, each register is 8-bit accessible, 16-bit accessible, 32-bit accessible, and 64-bit accessible. In the 32-bit mode, there are some exceptions where in some cases you cannot access some registers at the byte level. We'll look at it later. And when we compare this with our RISC-based model of the standard processor, there is a different mechanism how to process and implement branches. Because you have arithmetic logic unit, and when arithmetic logic unit executes some operation, you have some conditional code or some flux as a result of this operation. For example, overflow, carry bit, then information if it is 0, and so on. And they decide, or it was a standard in the fact for the complex instruction set processors, that those flux from the arithmetic logic operation were to be collected in some control status register. And then you can decide according to those indicators if you want to branch or do not want to branch. If you look at RISC-V, then there is no such flag register. So you need to do the actual comparison directly inside of the branch instruction. Or you can use SLT instruction, set less than, which sets a regular register, whole regular register according to the condition, tested condition. This decision to use the flux has advantages basically at the moment when you, for example, move a data to a register, you already can check if it is 0 and so on, and you do not need to add additional instruction. On the other hand, it has a disadvantage that all arithmetic logic operation in the fact has the output dependency to the flag register, which complicates the things. So from today, deeply superscalar processor, it is question if it is, I think that it is better to not have a flag register. ARM has flag register even in 64-bit mode, but they have a possibility for the arithmetic logic instructions to specify if the flag register should be used or if it should left be intact. So this way they can overcome those dependencies and so on. Anyway, so we have 8 registers in the 32-bit mode, and in 64-bit mode there are 8 more added, so we have in total 16 registers, general purpose integer registers. Then we have there a separate register for the instruction pointer or extended instruction pointer or RIP in the 64-bit version. And we have this flag register. And if we look what is stored in such flags, then we store there information about carry, about the parity of the last result on arithmetic logic unit, auxiliary carry, which is the carry from lower half to the upper half, and then we have there information that it is a 0 result and the sign of actual result. That's in the fact most significant bit. So it is this part. And auxiliary carry can be used for the BCD correction, so for computation in decimal format, and so on. And then the rest of this register, first 16-bit, now it is 32-bit register or 64-bit register, is a part which is not directly accessible to the user because it holds system flags. So, for example, if you want to disable interrupt, then you can clear this bit, and you are sure that a given sequence of the code would not be interrupted by the external event. Then there is possibility to invoke a trap for a step operation. Then there is input-output privilege level part, which allows to delegate ability to access input-output operation even from a given user-level program, and so on. And the actual code executes in 3 rings, or in fact 4 rings. Ring 0 to 3, and ring 0 is left for the hypervisor or operating system in the first design idea. 1 and 2 was left for the operating system, privileged libraries, and so on. And the ring 3 was meant for standard user programs. And only in the ring 0 you can manipulate with the memory management and with page tables and so on. So it was such separation of the privileges and ability to separate the processes. In the fact, those middle levels has not been used later, and in 64-bit mode they are not implemented at all. So we switch between the system mode and the user mode, so similar to the RISC processors, and then there are different special modes for the virtualization of the processor to have the ability to run 16-bit DOS, Microsoft DOS programs, and so on. Okay, as for the instruction set, there is a problem that there are more ways how to write the assembly code for x86. There is original Intel syntax which used for the movement to move data from one register to another or from memory to another register. It uses this form where it copies from to the target, where from is on the right and to is on the left. If you remember for RISC-V, then it has this order for all instruction except for the store-word operation, which has vice versa meaning of the argument. And then there exists a historical AT&T syntax which was used at the Unix computers before, and it was used even when the Unix system has been ported to the Intel architecture. And this mnemonic is that it moves from the left to the right, and the last character of the operation informs if it is quad word, so it means in the fact word in this case is fixed in the Intel architecture on the 16-bit. Even that today the actual machine word is 64-bit, the term word is used on the Windows and Intel fixed way bind to the 16-bit version. So we have 16-bit, byte is 8-bit, then we have a long, which is 32-bit, and then we have a Q as a quadruple and quad word, and it is a 64-bit version. And we can specify this directly in the move or in the each operation. So it is same as load word, store word, load byte, store byte on the RISC processors. It seems that it is more complicated, but on the other hand, in this Intel syntax, you have sometimes problem to specify what is the actual access size. For example, if you want to store a data constant to the location in the memory, then it gets quite complex. So you need to use something like Dword, PTR, and so on, such strange things, which can be expressed in this syntax by the letter specifying the size. For the registers, in the original AT&T syntax, the actual identifier without any prefix characters means the address to the location in the memory. So each register, when it is listed in the assembly source, has to be preceded by the % character. For the values, it is necessary to precede it by a prefix $ character, because in another case it means the address at this value, this memory location. On the Intel, if we want to specify memory location, we need to use brackets. And there are some examples. So for example, this means in the AT&T syntax, take a register ECX and move its context to the EAX. And in the Intel, it is ECX to EAX written this way. We can use offsets to the registers, same way as on the RISC architecture. So we can put there 3, which means 3 plus register, and move it to the register. But we can even use a complex addressing, because x86 is from the complex instruction set era. So it was intended that if we can encode, for example, the complex access to some structure in the memory directly in the single instruction, then it would be faster than if we build the address by a combination of multiple instructions and then access the register. So, for example, we can add those two registers when the second register is multiplied by 2. So, for example, if you have an array of 16-bit integers, and you have pointer to that array, so this is the pointer to some location in the memory, and in some another register you have the index, then you can say this index should be multiplied by 1, 2, 4, or 8, and added to the base, and this is the address which is used to load the data to a given register. You can even combine those even more complex way that you can add there even the offset. So in this case, for example, if you have a point structures which has 2 integers, so each has is x and y, x and y, x and y, then you can say, I have there a pointer to the base of the array, then I want to add the index, which is multiplied by 8, for example, and because I do not want to access directly the x, but a y, I want to add the 4. So you can encode so complex addressing directly into the each instruction. And the instructions are not limited only to the transfers. You can say about RISC-V and other RISC processors that those are so-called load store architectures. This means that only the small subset of the instructions can be used to transfer data from the memory to the register or from the register to the memory. And all other operation has to be proceed between registers. It has advantage at the time of exception during a memory accesses and so on, that it is much more simple. But on the other hand, you need to use more instruction for the same operation. So x86 define that we have the operation, for example, addition, subtraction, or that simple move, and then we can have a source and destination, And even in some cases, we can use even the string operations. In that standard arithmetic logic operation, it is, for example, add the, and we can use EBX to EAX. So this means we take the value from the address specified by EBX and add this value to EAX. You see that those are only two operand encoded into the instruction. So we have one operand which is input and output operand. We can use the operation to add the between two registers, register to register, or we can use even add the register value to a memory location. So all these combinations are valid. And then we have there a specific instruction to do an operation between two locations in the memory. Because you need quite often to copy data, for example, from one location to another location. And for this reason, we have there operations which are specific for the string operations. They have predefined implicit addressing of the registers. So they have a source index, or SEI, which means a 32-bit version, or RSI, 64-bit version, and the EDX, EDI, which is destination index. So this operation processes the operation between some location on the source and some locations in the memory as a destination. And this operation, those string operation, has the additional property that after each operation, they add the operand size to both pointers in the fact, and they can add the size, or if you switch a D flag in the direction flag in the flag register, then they can subtract this value, the size of the operand. And then they subtract a 1 from ECX register. So, for example, if you point to one location, we will have examples later, and to another location, set up the ECX that you want to copy some number of bytes, and then add the repeat prefix, then you have this combination, or in the fact, one single instruction which ensures and proceeds a whole data copy. So it looks nice. Okay, so it is the move string as string version. Do a compare. In the case of the compare, you can compare a source and destination location and add the not only a repeat prefix, but repeat on equal. So basically it repeats the comparison, and until there is no change, then it moves to the next and next location. So basically it can map directly to the MEMS CMP or STR CMP C-language functions directly in the assembly. So, okay, it has some ideas here, but the actual implementation is quite problematic. So, there is possibility only to load the value or store a value to a register. So it allows, for example, to fill a memory by some constant. Then there is a scan, which allows to find the location of the value stored in some register, and repeat input and output to the input-output address space to the peripherals. And we can use those possibilities to select if it should repeat according to ECX, or if the repetition can stop prematurely when there is not hold a given condition, fulfilled a given conditions. And there is an example. If you want to fill, for example, a block of the memory, some array, integer array, with value -1. So basically, you select that EDI, index register, destination index register, or pointer register, should point to the start of the array. Then you say how many locations we want to fill, and then you set EAX to -1, and then say I want to repeat so many times as is in ECX the operation store D, so this means a double word, so this means 32-bit value, to the given incrementing locations in the memory. So this is how we can set a whole array to -1. Or for example, if we want to find where is the end of the string strlen instruction in the fact, then we can say there is a start of the array. The maximum length of the array is 128 bytes. We want to compare against a value 0, and we want to repeat it on the byte entity level, element level, as long as there is, okay, and I think that it should not be a rep, NE, I think, not equal, as long as there is non-equality bit with 0 in ECX. Okay, as for the standard instruction, there is some examples. So it is ADD-Q. This means to add the quad word, so this means 64-bit value, and this adds the value 5 to the register 64-bit RAX. If you want to subtract from this register a value at the location specified by EBP -4, by the way, it would be probably some local variable because EBP points usually to the frame on the stack. So it is probably a subtraction of some local variable from EAX, 32-bit. This one, sub L, 32-bit, and it subtracts EAX from the location in the memory. You see EBP -4. So it, in the fact, takes the EBP -4, subtract the EAX, and store the result in EBP -4. You see there is a problem that we do not have 3-operand instruction. We have only 2 operands, so one is input, same as output. And we have there AND, OR, XOR, multiply and division, and integer multiply and integer division. For the multiplication, there are a variant which has a fixed output in EAX, EDX pair, in those registers which are used to return a value from the subroutines. And then there are some another which can overwrite a 32-bit register as well. For division, it is even more complicated. We have there another operation like the increment of the EAX of the register, but we can even say increment or decrement of the location at the some memory address. And we have there a standard logical shift left, or we can have there a shift right a byte, shift arithmetic write byte and rotate a write byte, and so on. So you can see that there are many variants of this operation, and they work a little different way. If it is shift right, then the value is filled by a 0 on the left, and we can specify how many positions we want to shift. If it is the arithmetic, that's same as on the RISC-V or other computers. In that case, we repeat the sign characters, so the sign is preserved. If we do a rotation, then in the fact a least significant bit, LSB in this case, if it is right, so least significant bit is copied to the most significant bit, so we can in the fact rotate the whole contents of the register. Sometimes if you want to combine more registers together, or if you want to process the last bit and do some operation according to its value, or somehow modify this value of the single bit, then there is the option to the rotation through the carry. So in this case, the least significant bit is copied to the carry flag, and the original content of the carry flag is put at the other end of the register. So there are quite a lot of such combination, how to process rotation and so on. As for the conditional branches, there is not directly encode the condition into the branch, but we expect that some previous arithmetic logic instruction sets a flag register. So basically it, for example, sets the result of operation is 0. And then you can test the result by this instruction jump if the result of previous operation was 0. Sometimes you do not want to rewrite content of any register by your operation. So in this case, you can use a compare operation, which in the fact subtract two values, but doesn't store any result, only stores the indicators for the 0, carry, overflow, and so on into the flag register. You can even use the test operation, which is equivalent, but instead of the subtraction, it does the AND. So if, for example, you end with some mask, you can check if the given bit is set. And after the compare operation or those test bit operation, you can test, for example, if the result is equal or it is the same as if the register is 0 or if the test is 0. So there are some of those names are aliases. Then we have there not equal, greater, and above, where a greater is signed operation and the above is it is bigger in the meaning of unsigned values. And there can be then great and equal, above and equal, less or below, below equal, and so on. And check for the overflow flag and for the carry flag and so on. So it tests for some combination of those conditions in the flag register, indicated in the flag register. Okay? If we look at this code, for example, if we want to increment some field in some structure at address ECX with the offset 10, then it is single instruction on the x86. On the RISC, we need to do the first load word, then add the 1, and the store value. So you see that it is more instructions. But the actual density of the code is questionable, because it seems for the first look that this should be a much more dense that x86 code. Sometimes it is. It is usually more dense than if you use 32-bit fixed encoding of the RISC instruction. But on the other hand, at the moment when you use a 16-bit aliases for the compressed subset or THUMB for ARM processor, then it is almost the same, and at the end, usually the RISC processors today wins. But okay, it seems that, for example, this implementation of the mem move operation in the FAC is much simpler than what you need to do on the RISC-V variant, where you need to load the value from one register, store it to the location by another, then increment both registers, subtract the one from the counter, and go to the loop. Internally, today, those complex instructions are not resolved by the microcode as it was done initially, but they are resolved by the conversion to the stream of the RISC-like operations. So internally, there is not big difference today. And the x86 has a special structure defined in the hardware. We have spoken about stack and storing the values onto the stack and restoring the values in the non-clobberable registers and return address register and so on. But there, in this case, there is a directly instruction to do this operation. You do not need to do it by the combination of more instructions. So if you do a push, then in the fact it pushes the value on the stack, which in the fact means because stack is growing down from the FFFF to a 0, 0, 0, then it means that push decrements the stack pointer, creates a new space, and stores the value to that location. And again, next push decrements the stack, allocates the location, stores the value, and so on. And if you do a pop, then you get the value, and then again get the value, and move the stack up. So this is last in, first out data structure in the hardware. You probably should know it. And this mechanism is used even later for the calling of subroutines. So stack implementation, we have there a special register, which is stack pointer, which points to the top of the stack. We have that push, which decrements the stack and stores the value, pop, which takes the value, and we can push, for example, the register on the stack. And it can be a 32-bit or 16-bit value, and we can store it and restore. There are the operations which allows to push a flag register and restore the flag register. In the case of user mode, that part which would restore a system part of the flag register is ignored. Then there is a push all and pop all operation, which allows to store a whole registers to the stack location. It is used mainly for operating system for the task switching and so on. And in the case of x86, when we call the function, then because they think that you usually need to store the return address anyway onto the stack, they combine the actual jump operation with the push operation. So the call on the x86 means that we store the previous value of the instruction pointer or program counter to a stack. And then there is a return instruction which does a restore of the and branch to the previous address from the stack. You can see that on the maps we do not have a return and call instruction. We use a jump to register and a jump and link for the call. On RISC-V there is the instruction call, but it is the alias to jump and link and store the return address to return address register. So it doesn't store directly the value to the stack. It stores to the register. On the x86, it directly interacts with the memory, which maybe for the leaf level functions for the last function called in the chain. It is a disadvantage because for this one, when we store the value in the return address register, we do not need to store it onto the stack. For the intermediate functions and calls, there is no big difference in this. And for the arguments in the 32-bit mode, we store all the arguments for the standard C calling convention on the stack. And we store local variables on the stack. So it is similar to the RISC-V with the local variables, but for the arguments, we use the registers on RISC-V. And for sure, stack size is limited, so you should not overload it by so many big arrays and so on. There can be some problem with recursion, stack overflow. There are some mechanisms how to extend the stack dynamically and so on. And now we look what is the function prologue or introduction and the end of the function. So standard function creates a stack frame on the stack. So if we call the function, then we have built there the list of the arguments. Then we use a call instruction. It stores a return address, alt AIP, and then we store the bottom pointer to the stack, and bottom pointer is used as the stack frame pointer in the fact, so as the frame pointer on the RISC. And we store the previous value here, then which points usually somewhere there, so we store it here, and set a bottom pointer to point to the location where the previous value has been stored. So in this case, if we add there this bottom pointer, then we know that first argument is each time on the offset +4 and so on. Because on +8, excuse me. On the +4 is the previous program counter value, and on the next one is the first argument. And then, when we want to finish the function, we can restore a bottom pointer from the stack pointer, then restore the previous value of the first we restore the stack pointer to point to this original location of the bottom pointer. Then we restore a previous bottom pointer for preceding function. And then we call a return instruction, which pops the previous value of the program counter from the location in the memory. And because this last combination of those two instructions is often used, then there is a special instruction which is called a leaf, which combines those two instructions because it is complex at architecture. And during running of the subroutine, you know that the local variables can be put on the stack below the address of the bottom pointer. So those are location of the local variables. And this is the location of the first input argument and second and so on. I have already shown this in the previous lecture, but you can look at it again. There are some typical combination. For example, if you want to clear a value of the register, then if you do exclusive OR of the register with itself, then you know that the result is a 0. So it is faster than to use the instruction which needs to store somewhere the immediate operand. So it is faster. There is another instruction which is interesting, and it is load effective address, because we have so complex mechanism how to compute those addresses into the indexed arrays and so on. And sometimes you want to reuse such address more than single time. Then in such case, it works to store the result of this effective address computation to a register. So it is load effective address. And in the fact, if you see this instruction, then it doesn't override the ESP with the value on the ESP minus 12, but in the fact, it overrides a ESP only by the ESP minus 12. So it is the option how to write the arithmetic operation that you use this special load effective address instruction. And in the fact, it is only way how to work with 3 operand arithmetic operation on x86 in most cases. Then there is a floating point register, floating point coprocessor, and even from those original days of 8086, it was quite capable. It can work with single 32-bit floating point representation, 64-bit, and even with extended 80 bits format, which has a higher resolution than the standard IEEE 750 for implementation and so on. And in this case, we have 8 registers in the coprocessor, each with 80 bits length, and the organization of those registers is on the stack basis. So it is in the fact a stack computer system. So if you proceed the operation, then the operation takes the value from the top of the stack, then combine it with some another location on the stack, or maybe with the second next on the top, and then it push the result on the stack. So this way you can write relatively complex expressions without a need to address the arguments too much. You need only the address arguments when you load the values from the memory to the coprocessor, but then you can do a sequence of the operations without the need to specify the operands. And originally it was a separate chip, but from the 486 day it is directly on the D, and it supports many operations, and those floating point operations add with the letter F. So, for example, we have there the operation to load the value from the memory and push it onto the top of that 8 location stack of the floating point processor registers. Then store to a memory without the pop or without the pop of the top of the stack, so releasing the location. We can even take a integer value from the memory and convert it to the floating point and push it onto the stack, or we can store the value, round it as the integer. It can be with a pop, and we can do, okay, it can be a fixed or it can be a rounding. So there are the options. And you can address a location inside this stack as the stack top, 0, or 1, and so on, next one under the top, and so on. So during the operation, if you, for example, want to add, you can add. If it is without the argument, it takes the top of the stack, next location on the stack, compute it and store it to the top of the stack. In this case, we are not speaking about the stack in the memory, about the stack of the registers inside the floating point coprocessor. And there are those different possibilities how we can combine the values. So this one is directly with the top of the stack. Then we can combine it with another location into the stack not only the second next value, we can store the result into some another register, then onto the top of the stack. So initial idea that the stack organization would help a lot and short the programs has proved to be complicated, and at the end we have quite complex operation which do a different combination of manipulation with the stack and pushing the data to the different location of the stack. Okay, we have there the addition, subtraction, we have there reverse subtraction when we can subtract the top of the stack from some another location onto the stack and store the result onto the top of the stack. We have there a sine, cosine operation. We have there a tangent, arcus tangent, a tantu. So there are many different operations. There are even some special instruction to load some well-known constant like a p and Euler numbers and so on. And if we want, for example, to compute this expression, then we first load the memory location when we have the first operand, or in this case constant for sure. This would be evaluated by the compiler at compile time, and there is no need to compute it and floating point unit, but it is an example. So this way we load the first, then we multiply with the next one location in the memory and store the result onto the top of the stack. Then we load the third value, compute the sign, which pops the value from the stack, and push the value, which is the result of the sign operation. Then we can do the add and pop. So it took the two values from the stack. So in the fact, it takes the result of the sinus and this multiplication, and then we have the result and store the result to the memory. So it is for the floating point operation. Then there came an era when people wants to hear music or look at the video. And at that moment, you need a fast processing of the images and of the stream of the points or sound samples. And you usually need to do some convolution. For example, you need to do a Fourier or cosine transformation and some scaling and brightness compensation and so on. And in such case, you want to do a same operation with consecutive pixels. And for this reason, it worked to do some single instruction, multiple data processing with the data which are read in the single go. And Intel has found that they have 64-bit registers in the floating point unit. And if you want to run a multimedia, they decided they do not need the floating point for this. So when you start some multimedia sequence or subroutine, then you can switch a floating point coprocessor to the multimedia extension in the fact mode. And in this case, those 64-bit registers can be used to store, for example, 8-bit values. So if you use those operations, you can do, for example, your sharpening of the image, homework number 2. You can do it faster because you can proceed the operation on the multiple pixel at the single go. Okay, it is not so easy, but it is possible to use even this extension. And you can have 8-bit, or you can have 4 16-bit, or 2 32-bit integers, and you can do the parallel operation. So it is parallel add, parallel subtract, parallel, and so on. We look at some of those operations, so we can use those different operations. And okay, if we compare it with the RISC-V, Then on risk 5, we have the floating point which separate 32 64-bit or 32-bit registers. So on the RISC architectures, we usually have a same set operations as or similar mechanism to operate on the floating point like on the integer. In the fact, even on the RISC architectures for floating point operation, there is a special flag register. In this case, the flag register is used even on the RISC because it can help the information that there was not only the overflow during the last operation, but that there was overflow in the sequence of operations and so on. So for this reason, we have there flag registers, and this is how it works on the RISC-V. So we have floating point add, and we can, with this .s and so on, we can specify it is single or double and so on. So it is only a short note how it works on the RISC processors. And now we return to those parallel operations. RISC-V has a vector extension as well, so there are the alternatives to this multimedia extension of Intel on almost each architecture today. Anyway, parallel add word. So what it means, we have 64-bit register, and we divide it to the 4 16-bit registers. And if we run the operation between the, again, we have only a 2-operand encoding, so this means that one instruction is, one register is input and output, and the second is input only. And we do the addition between the corresponding words in the register and store the result here. And we can have addition which overflow standard way like for the integer arithmetic, or we can have a saturated version which ensures that the result is saturation. Again, if you remember, there is a problem for the, there can be the overflow in your sharpening code, and you need to limit the value to 255, because if you do not limit it, then you can get into the situation when the result is incorrect. For sure, it is not fully correct even if you saturate the result, but it is better to stay in the white color than to flip the given pixel to the black one or some random value. So this is a reason why we have the saturated version, usually for multimedia. We have even the multiplication. But for the parallel multiplication, you see that there is a problem, because if we multiply two 16-bit parts of the register, then the result can be up to 32 bits. So in this case, it is solved such a way that those two 32-bit results are combined together, because you anyway usually want to compute a scalar product of the vectors, because it is the most common operation. I'm not sure if you have already something like Fourier transform, cosine transform. Have you? Who knows Fourier transform here? Okay, no. Okay, so you will have it. So basically, it is based on the convolution. So in the fact, all this is based on the fast computation of the scalar product of the vectors. Scalar product of the vectors should be known to everybody here, I hope. So basically, we put together the corresponding elements, multiply them, and sum the results. So this is the partial sum. So it is multiply and add. We can use sometimes a version when we keep only the low part of the multiplication, or we can keep a high part of the multiplication. If it is attenuation, for example, where we want to use the value from 0 up to almost the 1 for the fixed point computation, then in such case we can keep a upper part of the result, and in the fact we do not need to care about a low part. It is for the fixed arithmetic computation. Okay, so those are such combinations which we can do. And we look there at the one example. It is from the long presentation of the Konstantin Levit-Gurevich, which was one of the developers at Israel, and it is professor on Israel University. And there is an example, because if you have the image, for example, with a green keying, and you want to combine it with some live stream from the seashore, and combine the result, your report here, and the seashore, then you have a problem that if you compare to the value of the pixel to the green, and then use the if statement, so basically if you do this one, then you have a code which is controlled by input data, so there is high risk that no branch predictor can predict it correctly, because it doesn't know exactly a whole image and where it should switch from one and to another and so on. So it is a big problem. And in such case, I have already shown how it is possible to write a code which eliminates the condition, for example, that computation of the maximum or minimum value and so on. I think that I have shown this example. Okay, and then we can use a multimedia extension here. Expect that we have 16-bit encode colors. We read the 4 16-bit pixels, and for the first X pixel, we know that it is green. Second is not green, here is green, and 4 is non-green, as the example. And we want to compare it with a green. What happens? In this case, it happens that this kind of the comparison doesn't set a 1 or 0, but sets a mask. So when there is a match with the color, then the whole corresponding part of the 64-bit register is set to FF. When there is not match with the green, then it is set to zeros. And so on, ones and zeros. And now we use a negative end with the input image. So in this case, those pixels which has been green are masked out, because we use this input as flip it to the zeros and this one to the ones. So x1 is eliminated, x3 is eliminated. And you see, in the result, it is a 0. Then we take the mask, which we have computed this way, and use it in positive way to mask the Y image. And in this case, we mask out those points which are overlapped by non-green points in the original image. So basically, we keep only those which has been green there. And then we do a parallel OR of those two vectors, and we get that combined image directly which we want to have. So this is example how we can use a parallel operation. It is exactly the same example I've written here. And we can do it this way and enhance the throughput. And there is only the final branch when we, at the end of the loop, so when we go through the loop, there will be only the single misprediction at the end. Okay, then there was an extension which is called 3D-Now, because it became evident that even a multimedia operation will need a floating point operations. For example, if you have a game in 3D space, then you need to compute a affine transformation of the vectors. And for this, it is used the mechanism which use matrices 4 by 4 floating point numbers in this case. And this allows to implement the affine transformation. And you want to do this matrix computation, so 16-element matrix by 4-element vector fast. So AMD started with Oven because Intel was not providing a guideline how the instruction set will be extended. So AMD came with their Oven extension called 3D Now, which allows to operate on those floating point vector representation. Later, Intel came with streaming single instruction multiple data extension, and in this case, they decide that they add the additional registers. So they do not use those registers which they have in the floating point coprocessor, but added the another set of the registers, which are 128-bit each, and allows to store up to 4 floating point single operands or 2 double operands, and can compute the operation in parallel. Today, do you know what is the actual maximum size of the vector operations on the Intel? Have you heard it? It is today we have AVX extension which can work with 512-bit entities. So you can do such multiplication and operation with quite a lot. It is 500, it is 9. So if we want to process it with the 32-bit singles, so it can work with 16 single floating point elements vector at a single go. So it is another extension which is used. So we have there again the operation which can add the corresponding value, multiply the corresponding values, and so on. And there are even the operation which can compute a minimum and so on. And initially the SSE started for the floating point representation, but today it can work even with integer. So today most of those complex operations are executed on this subset of instruction set, and SSE registers are even used to pass arguments to the function. So floating point arguments are not passed in the 64-bit mode on the stack, but inside of those registers. And the number of operations added by each revision is quite large. Again, it seems that this encoding is not big win. The ARM has used this Neon operations extensions for the multimedia operations, but even it starts to copy the mechanism of vector extension when you can specify the size of the operands, which was initially used in 60s by the Simon Cray in the Cray supercomputers. Then it was skipped, and this multimedia with fixed length has been used. And today, scalable vector extensions are becoming popular. It was partially reinvention of RISC-V architecture, but it seems that it is used by the ARM, and it is questioned what x86 can do with this. Okay, so it is a basic overview for the x86. We have already something about the calling convention. Maybe we can look at it a little more. Maybe I have there a full presentation of Konstantin Levit-Gurevich. So we can look onto the encoding of the x86 instructions, because your fourth homework is to decode x86 or RISC-V or MIPS program. You have it in all of those architectures. So to have some basic idea how the encoding of the complex instruction in the case of the x86 look like, then there is an example or some description. So basically, the instruction format of x86 has a 1 byte which specifies the start of the opcode. It can be extended, so even the opcode, the operation code, which encodes if it is addition, subtraction, branch, and so on, can be extended up to 3 bytes. So this is the operation code. We can add the prefixes before the instruction. So those are the prefixes repeat until the CX register is not 0 and, for example, a result is EQL or something like that. Then we can have there 1 byte for the standard access to the register mode, and the second location can be memory or the register. Then we can have there the scale base index byte. Then we can have there a displacement, which can be not only that fixes 12 bits like on the RISC-V, but it can be even up to 4 bytes. And then we can have there the immediate value, which is again up to the 4 bytes. And the minimum instruction size is 1 byte, and maximum one is 15 bytes, and in 64-bit mode, even 1 byte more, so it is 16 bytes. So you can imagine how complex it is decode, so complex instruction. And we have there this description. Opcode is some constant. Maybe it can encode even directly, increment the top of the stack, and so on for some instruction. But mostly it is do something like addition. And then we have there this second byte, mod RM, and this part specifies the 1 register or extension of opcode if it is a single operand instruction. Then there is this mode which specifies if the second location is a register or pointer to the memory. And through some registers, if you select the correct mode, you can point directly to the memory with this simple variant of the instruction, or with the single extension word. But at the moment when you want to combine index and base, then you need to select that it is special mode with special this combination RM, and then add another byte which specified if the index is multiplied by 1, 2, 4, or 8, and what is the index register and what is the base register, and so on. We look how the actual instructions looks like in the memory. So there are the instruction which has opcode. It is what you will see in your dumps of the programs. Then this is the case when we have a mod RM. In some instruction, for example, like to move to the EAX, we encode this information that it is moved to EAX directly to the opcode. So it is not necessary this one. Then we can have there the immediate value. In this case, for example, if we want to store a 0 to EAX register, you see that there are 4 bytes additional with the value 0. As you see, if we use a exclusive OR to 0 the EAX register, it is much, much shorter than this 5-byte instruction. In this case, we have there a different offset or different values which are stored to the memory and so on. This one is AND, which is signed extended. In this case, we have only the addressing subtraction of two registers, so it doesn't need any extension. In this case, when we want to store the value to ESP multiplied by 1, then in such case we even need to use this additional byte. And then there are displacements. So for example, if we want to call the subroutine, we can put there a relative difference of the actual instruction address and the target instruction. And some instructions are quite simple, so they do not need to encode any additional information. So there is another instruction. So for example, this is the instruction, increment the value, and there is a location. So this combination says increment word at the address given by BX and DI destination index registers. So those two are add, this is multiplied by 1, and at this address. But we can add there a prefix. So for example, we can say it should be, increment should be repeated as long as the result is 0. Then we can say we want to lock the memory bus to ensure that the instruction is run as the atomic one. Then we can say that we want to use a segment override, so it means that it is not at that standard data segment location which points to some object in the memory, but that it should use FS. Then we can say that it should not run in the 32-bit standard size of the operands for the 32-bit mode, but that we want to limit the address to the 16-bit. So you can see that this simple instruction with all those prefixes has quite complex encoding. Then there is a more usual instruction, move the value from some of those registers to the byte register accumulator low or AL register. So we specify operation move byte from memory or register to the register. Then we specify by this combination we want to use AL register, and that we want to address memory by this complex mechanism when we combine two registers, and then we have there actual combination of those two registers. So you see again quite complex instruction. There are the tables which show how those all encodings are implemented, and as you can find, it is not fully orthogonal. So there are exceptions and so on. There are more examples. You have this presentation in the additional materials to the lecture number 11. Okay. Protected mode and so on. The addressing is relatively complex, where the first we do the addressing not through the page table, but through some table which describes objects which can be selected by the selectors. Then there is an offset up to 32-bit. We get the linear address in our address space, and this linear address is then translated through standard 2-level, 3-level, or 4th-level page tables to the actual start of the page and the offset of the page. So this part, it is a standard one. This is quite complex, and in the 64-bit mode, it is not used. We have already seen how the registers looks like, and we have already discussed it, even 64-bit ones. And in the case of AMD extension of a 32-bit Intel architecture to 64-bit, they decide that they extend the general purpose GPR, general purpose register, and SSE registers count to the 16 because 8 registers is a very low amount and there is big pressure on the register allocations inside the compilers and so on. But if we add another 8, it somehow can work. And they decide that they will use the same instruction to access the first 8, and then they use an extension which allows to use the rest and allows to address even the first part as the 64-bit. So by default, you address the registers as the 32-bit, but you have the option to address even 16 registers with 64-bit addressing. And there is an addition that original architecture was not orthogonal, that some registers was not accessible by the size of 1 byte. So they decide that each register has to be accessible even like byte, because if you want to use it to hold the character, for example, and so on, it is easier to allocate a whole register than to use the half register in EAX and so on. So, and how they achieve that they can use the same encoding of the instruction to encode this bigger number of registers. Okay, there it is declared that even those registers which are not accessible by byte are already accessible by byte in the AMT 64-bit mode. They have got rid of all that complexity with descriptors and objects to define 3 rings and so on. They have only system and user and so on. And they extended some registers to 64-bit. It is not so important. There is possibility to switch between the 32-bit mode and 64-bit protected mode. You need to start the system in the 32-bit protected mode, and then you can go to 64-bit. And even in 64-bit mode, you can switch to the 16-bit compatibility mode for a given user space process. So standard process is 64-bit, but you can have 32-bit or 16-bit process which maps to subset of virtual address space for the given subset and so on. So it is possible to run even the original 32-bit programs without the recompilation on the 64-bit operating system. There is how we switch to the 64-bit mode. The registers are skipped. In the 64-bit mode, we have now these selectors and so on. And address space is extended to the 64 bits, and they decide that only part of this address space is available. So basically, you do not want to work with 64-bit physical addresses because you do not have so much memory. And even the virtual addresses, when they are 64-bit, would result in the, I think, 6-level page tables, and it is too much. So they decide that only the addresses which start with the same bit, sign extended value, can be used. So basically, we sign extend a 48-bit virtual address to 64-bit virtual address, but it is sign extended. So 1/2 of address space is used for the operating system, or one, not half, because top part of the address space can be used for the operating system, bottom part for the operation, up to 2 power 47, and that middle part is invalid range. And they decide that if they need, they can enable more levels of the page tables, and then they can reuse even this part. Until now, extended the addressing from the 48-bit to plus 9-bit, so 48, 57, I think, 56 or 57 bits. by adding another level of the page table. And they use, by default, the 4-level page table. So you probably should know this picture. It is a picture which you have seen. You've seen it with 2-level. Now it is a 4-level. There is something about paging that you can have huge pages, that if you have a big linear range which you need to rem up, that it is not necessary to add there all levels of the page tables. And the encoding, how to encode those instructions when we want to keep the compatibility and decoder with the previous architecture compatible. They decide that there will be the additional prefix. They use for this prefix the opcodes, which was used in 32-bit variant for the increment and decrement operation. So they declare this that the increment and decrement has to be done through the addition and subtraction, and define that this extension, this rex prefix, will be put directly before the opcode. So it is not possible to put this at arbitrary location like other prefixes, but it has to be directly before the opcode. And the rex prefix has 4 bits predefined, and then it specifies if the operation should be executed in 32-bit or default 16-bit byte mode and so on, or in 64-bit mode. And then they extend the address of the register by those 3 bits. So in the fact, when you want to address the location, then for example, if you have this move to R8 from the R9, so the registers which are outside of that first 8 registers, then you can use this prefix, specify that it is 64-bit operation, and substitute those 2 bits to combine them with the location of the registers provided by the other extension byte. And again, this is another combination, and even this most complex one, when you have a register, another mode to specify that it is scaling, index, and base register, can be extended by this bits from this REX prefix to allow the full addressing of all 16 registers. So it is interesting. There are the examples how it works and so on, what are the default operand sizes and so on. So I stop here. You have the homework number 4, which uses the 32-bit x86 code. You can decode it from the RISC-V. For the exam, we can ask for the calling convention which uses a stack to store the arguments. So this is a mandatory. The rest from this lecture is mostly for your information. Okay? So thank for the attendance.